Hello. Okay. So, a very good morning to all of you, to all the distinguished guests and the students. And also we have people from school here. First of all, I'd like to thank the organizers and MMU for having me here. It's really great to be back. I think I spent around 9 years of my life here, 8 years in cyber and 1 year in MMU Malacca. Okay, and I think I have very fond memories of this place, you know. And I think many of you will agree with me that university time is one of the best times of your life. Okay, I met, a lot of my best friends today, I met them actually here. And those of you who know me will know that I also met my wife here, okay, in MMU. Right? And yeah, the experience here has shaped me a lot. So yes, it's great to be back, and I almost got lost because I couldn't recognize Cyberjaya roads anymore. And it's great to see all of you here, and I hope you'll learn something, okay, today. And today I want to invite you to join me on this journey from Cyberjaya to the edge, okay, or the event horizon of a black hole. Okay? Now, sorry you have to do a quiz, huh? Okay? So does anybody want to tell me, what is a black hole? You can just shout it out. Okay, there's someone there who wants to say. Okay, something that has an event horizon, it has an inside and outside. Okay, anything else? Anybody else want to try? Yes, there's one back there.
Space that has a very condensed mass, and because of that very, very large mass and less space, it attracts anything that passes by, even light cannot escape it.
Okay, so thank you very much. Yes, it's a place where, the gravity is so strong, right? Okay, so a black hole, okay, is a region in space, right, where the gravity is so strong, not even light can escape. That's why we call it a black hole, because no light can escape, right? So it looks black, all right? Okay, what happens if I take a ball? Okay, imagine I have a ball here and I throw it up into the sky. What's going to happen? The ball will eventually fall down, right? If I throw it a bit harder, what happens? The ball will fly maybe higher. Eventually it's going to fall down again. How fast do I need to throw the ball before it escapes the Earth's gravity and goes into space? About 11 kilometers per second, right? That is what we call the escape velocity. Okay, to escape the Earth's gravity, you need to travel at least 11 kilometers per second. To launch a rocket into space, that's how fast it needs to go. Okay, imagine you are a superhero, okay? Maybe you are Captain Marvel or something, and you're on the surface of the sun. Now, the sun is much heavier, okay? It's more massive. How fast do you need to travel to escape the sun's gravity? Okay, if Captain Marvel wants to escape from the sun's gravity, wants to fly away, she has to fly more than 600 kilometers per second. Okay? Now imagine, okay, a region in space where to escape the gravity is so strong, not even light can escape, and light travels at 300,000 kilometers per second. Okay, so light can travel around the Earth 7 times in 1 second. Okay, and even light cannot escape from the gravity of a black hole. Okay, and this boundary, okay, someone mentioned this, the event horizon. Okay, this is kind of the point of no return. Once you pass through the event horizon, okay, even if you travel at the speed of light, you can't escape. Okay, and Einstein tells us that nothing can travel faster than the speed of light, so nothing can ever escape a black hole. It is a one-way ticket out of our universe. Okay? And a lot of people have this misconception that black holes suck. Okay, black holes don't suck. They are not like vacuum cleaners where they're sucking things in. Okay, just like how the Earth and the sun doesn't suck anything, but if something goes close enough, eventually the gravity will pull you in, okay? And usually we have gas and stars and things that are falling into the black hole. Okay, and all this gas, we call it the accretion flow. Okay, and they are sometimes so hot, okay? They shine very brightly, okay? They can be up to like billions of degrees, okay? Very hot, okay? So today I'm going to give a few take-home points, okay? If it's boring and you fall asleep, as long as you remember these 5 take-home points, okay, I'll be very happy, right? And the first take-home point is, black holes are simple, okay? Now, humans, we are complex. If I tell you to describe a person, right, there are many things you can say. How tall is the person, how heavy, what color is the hair, or whether got hair or don't have hair, all right? But black holes, okay, there's this theorem called the no-hair theorem. Black holes have no hair, okay? And this is what happens when you have dirty old men giving names to things like in astronomy, okay? And what this means is, this theorem says is that all black holes can be described by 3 properties, okay? Their mass, how heavy they are, their charge, electrical charge, and their spin. Okay, and the universe is mostly actually neutral, so actually there's no charge at all. Mostly what we know, okay, we actually don't know much about black hole spin, but we do know about black hole mass. Okay, how heavy the black hole is, right? And that's why we have classified black holes into 3 different types. Okay? One is what we call the stellar mass black holes. Okay, these are black holes which are typically they're heavier about stars, okay? Similar weight as stars. Okay? And these black holes have a mass of about 5 to 100 times what we call the solar mass. This is the weight or the mass of the sun. Okay, and to remind you, this is how much our sun weighs, 2 with 30 zeros behind it in kilograms. Okay, and these typical stellar mass black holes, they are 5 to 100 times more massive than our sun, okay? And these black holes are usually formed when a star reaches the end of its life, it explodes, it collapses on itself, and you get this black hole. So those of you who watched the movie Interstellar, right, Gargantua, that black hole, okay, that is one of our stellar mass black holes. Okay, secondly, what we have are called intermediate mass black holes. These are about 100 to 100,000 times the mass or the weight of our sun. Okay, scientists are still debating. Some people claim to have discovered these, but so far it's not conclusive. Okay, we don't know if they are out there. Okay, now the last kind of black holes, which are my favorite, because the last 10 years I've been studying these things, okay, are what we call supermassive black holes. Okay, these are 1 million up to 10 billion times heavier or more massive than our sun. Okay, these are huge things, right? And now we believe that inside every galaxy, okay, including our own Milky Way galaxy, has one of these supermassive black holes. Okay? So that's number 1. Okay? Black holes are simple, right? Number 2, black holes exist. Okay, that's my second point today, right? And not just in my bank account. Okay, there are real things out there. Okay? And the first kind of early evidence we have that black holes exist come from these objects we call quasars, okay? These are very distant objects. We find out that they are actually in the centers of galaxies, far, far away, up to billions of light years away. Okay, and sometimes they produce what we call these little, can you see this? Beam of light, okay? We call these jets, okay? And what are these? Okay, it turns out, okay, the best explanation for this is that there is a supermassive black hole in the center of the galaxy. There's gas. Okay, so this is just an artist's impression, okay? So there's gas that's falling down into the black hole. Okay, just like when you on the tap, the water goes in, and in a circle, right, they're falling down into the black hole. And because of friction, they are heating up to billions of degrees. And some of this stuff doesn't fall into a black hole. They get ejected, by magnetic fields. And they get ejected and launched as these jets that sometimes travels up to tens of thousands of light years, okay? And the only way we can explain these things are if these are powered by black holes, okay? And here's a picture from Hubble Space Telescope of a very normal galaxy, okay? This galaxy has about 100 billion stars inside there, okay? And this is what you see with a normal optical telescope, okay? Now let's say you can tune your eyes, okay? When you're in the car, you drive, you can tune to different radio stations, right, okay? Let's say we can tune our eyes to observe at frequencies in radio. Let's say you can observe radio. Okay, what do you see? These are real images, okay? These are not artist's conception, okay? This is what you see in the radio, okay? Inside, we have what we believe is a supermassive black hole, okay? And the black hole, close to the black hole, is shooting out these jets, okay? Sometimes moving very close to the speed of light, okay? And these jets travel for tens of thousands of light years, Okay, and then here they interact with the intergalactic gas, okay, and they form these lobes. Okay, and this was some of the first evidence we have that black holes exist. Okay, of course, the strongest evidence we have that black holes exist come from this, okay? It's inside the center of our galaxy, okay? Now here you see we are zooming into the center of the galaxy, closer and closer, okay? And this black stuff is actually all dust, and the dust is blocking the light from the center of our galaxy, okay? Now, as we zoom in and in, okay, we can't see the stars in the middle because of all the dust. But if you can see infrared actually penetrates through dust, okay? So if we switch our eyes to see infrared, we can actually see all the stars in the middle, okay? And scientists have been tracking the stars in the center of the galaxy for decades, okay, 10, 20 years. Okay, they look at the orbits of the stars, okay? And they see the stars are actually circling around this dark object that doesn't produce any light at all, okay? And based on how the stars orbit, by looking at the speed at which the stars orbit this object, we know that the mass of the object in the middle that doesn't produce its own light, okay, has to be about 4.2 million times the mass or weight of our sun. Okay, so this is a giant, 4 million times the mass of our sun. Okay, and all of this is within a very small region, okay? And the only explanation, the only thing that can be inside there is a black hole, okay, a supermassive black hole. Okay? And then more recently, I think 2 years ago, some of you heard about these gravitational waves, right? And of course, they won the Nobel Prize for this discovery. Okay, what they detected was gravitational waves, which are actually kind of ripples in space-time itself. Okay, traveling for billions of light years to our gravitational wave detectors here. And what they detected are two stellar mass black holes, okay, the small kinds, colliding with each other. Okay, so black holes are simple, black holes exist. And now I move to my next point, okay? Black holes are important, right? Important for the universe, but also important for you and me, okay? And here's why, okay? Now what we've discovered in the last decade or so is that black holes play a very important role in the evolution of galaxies, okay? So I show you these jets, right? They come out close to the black holes. What you find out is this, these jets sometimes are so powerful, they heat up the gas in the entire galaxy. They heat up the gas in nearby galaxies as well. And when gas is hot, they cannot form new stars, okay? For galaxies to form stars, the gas must be cool and the gas can collapse together to form stars, right? But when it's hot, stars cannot form. And now we know black holes play a very important role to shut down the formation of stars in galaxies. Okay, so in the evolution of the universe, you know, after the Big Bang 13.6 billion years ago, about 10 billion years ago, okay, about 3 billion years after the Big Bang, that's when most of the stars in the universe was formed. Okay, so most of the stars you see in the universe today, when you look at the sky, most of them were formed about 10 billion years ago, okay? And what happened after that? The stars formation started to decrease and decrease. And because black holes were becoming active as well, and the black holes, when they're active, they push out all the gas, they heat up all the gas, they stop stars from forming, which is why now the universe is pretty quiet. Okay, like our Milky Way galaxy forms about an average 1 star in a year. Okay? Now, closer to home, right? How many of you use Waze? Anybody use Waze to drive? Okay, how many use Grab? Okay, all of us use, huh? Now, how does Waze and Grab know where you are? You know, to show you the map, to show you the directions and all that. We have what we call GPS, right? So all of us are familiar with GPS. Okay, now how do GPS work? Sorry, so you have a network of satellites, right? So GPS works because there is a network of satellites in space. Now the satellites, they can triangulate, okay? As long as you have more than 3 satellites, they can triangulate your position and tell the system, okay, the GPS system where you are. Okay? Now, but for the GPS system to know where you are, they also need to know exactly where the satellites are in space, right? Otherwise, they can't tell you where you are, okay? But the satellites are in space. How do you tell the satellites? How do you tell the system where the satellites are? What is your reference point? Okay? On Earth, we have landmarks, we have your coordinate system. But in space, how do you reference? How do you say the satellite is here or there or whatever? Okay, we have what we call the International Celestial Reference Frame. Okay? Now, what can you use as a reference in space? Can you use stars? Okay, technically you can use stars, right? But stars are not very accurate because the stars are also moving. They are not fixed in space. Okay, all the stars around us are actually moving. Okay, they are moving around the center of a galaxy, okay? So stars are actually moving. You need something further away. Okay, so when you have something further away, it's much better to use as a reference because they always look like they're not moving, right? When you're driving in the car, okay, the things that are nearby you, the trees, the buildings, they move by very fast, right? But when you're driving, when you see the moon, it looks like it's stationary. Why? Because it's very far away. Okay, it feels like it's stationary because there's not much change in angle. Okay, so the more far away something is, the better you can use it as a reference point. Okay, so stars are not so good. So you use something very far away, which are these supermassive black holes. Okay, the quasars I was talking about. They are billions of light years away, and they always appear to be stationary in the sky. Okay, and because of that, we use these. There are about 3,000 to 5,000 quasars where we have measured their exact positions, and we use that as a reference point for the celestial reference frame, for the coordinate system, for the satellites, which we all use for GPS. So it's quite amazing, right, that something that's billions of light years away, right, can be used, okay, for the GPS system to tell us, where we are, down to accuracy of meters, right? So that's crazy, okay? And because we know the positions of these objects, we can actually use them in a reverse way, okay? So it's not only astronomers who use telescopes. Geophysicists also use telescopes, okay? And by pointing the telescopes at these distant quasars, okay, we can actually measure the accuracy, the position of the telescopes down to millimeters. Okay, and geophysicists use this to actually study tectonic plates, continental drift, okay? And so people use a combination of GPS and telescopes to study how the continents are drifting from each other. Okay, and the telescopes method, okay, using quasars, black holes, this gives you the most accurate measurements, okay, down to millimeters. You can measure changes in the position of the telescope, okay? And something even more interesting, okay, all of us know what is Wi-Fi, right? Okay, now how was Wi-Fi developed? Okay, I think it was in the 60s, 1960s or early 70s, okay? Stephen Hawking came up with this theory that black holes actually can evaporate. And after they evaporate, they explode. Okay, and so there were a bunch of radio astronomers in Australia. Okay, one of them is John O'Sullivan. Okay, and they said, okay, why not let's go detect these exploding black holes, okay? But they faced a problem, okay? When these explosions happen in space, the signal travels so far away, when they reach the Earth, they reach the telescopes. Some of these signals go directly to the telescope. Some of them bounce off the ground and bounce off the trees and all that before they reach the telescope. And this actually distorts the signal, okay? And they found a way to solve this problem, okay? And they patented the technology, okay? Now, unfortunately, they didn't find any exploding black holes, okay? They didn't find any, but their patented technology now impacts all of us, okay? In the early 90s, I think, when people started developing Wi-Fi, they faced the same problem, okay? When you're indoors, you transmit signals. The signals get bounced off the corners of the room, the walls, and whatever. Okay, and it's the same problem, and they realized that this problem has been solved in radio astronomy. So they took that technology and put it into all the Wi-Fi systems. Okay, it's now inside the IEEE 802.11 protocol for Wi-Fi. Okay, and what happened? The Australian people realized that they are not getting the proper credit. Okay, in 2009, okay, the government of Australia, they sued Intel, Toshiba, Netgear, Dell, Nintendo, Buffalo, D-Link, basically all the big guns, the big companies, they sued them because their thing was already patented and they were not getting the rewards, okay? And in 2012, I think they sued even more, okay, Lenovo, Acer, basically any company that uses Wi-Fi in their devices was sued by the Australian government. And eventually, all of them, most of them went settlement out of court, okay, and the government actually got back close to about 400 million Aussie dollars, okay. This one 229, but 2019 they got another 200 million. Okay, now all this research is actually going back to radio astronomy research in Australia. So, every time you turn on your Wi-Fi, remember that Wi-Fi came about because of a technique that was developed in radio astronomy, or because people wanted to search for exploding black holes. Okay? Okay, so now I move to my take-home point, okay? And I mentioned that black holes exist, right? So now my part 4, my take-home point 4 is that we have actually captured the first image of a black hole, okay? And I believe, okay, of course we can't see the black hole itself because light cannot escape, right? But we are seeing the light from the gas around it, okay? And I believe most of you have seen this picture, right? Anybody hasn't seen this yet? So the people who are doing some statistics, I don't know how they calculated this, but my European colleagues in the European group, they tell us that around 5 billion people in the world have seen this image. Okay, and I don't know how they came up with that. Okay, what is this? Okay? We say this is the first image of a black hole, right? But what are we seeing? Okay, basically we have all this gas that is falling into the black hole, and they emit this bright light, okay? And this light or photons, they travel around the black hole. Some of them travel close enough that the light gets bent around the black hole because of gravity. Okay, you get bent around the black hole, but if you go too close, some of this light falls in. Okay, so the light that falls in, you see it as a dark patch, okay, which we call the shadow of the black hole. And around this is the light that is bent toward us from around the black hole. We call this the photon ring. Okay, this is a simulation of what we think it looks like. This is our actual image. Okay, a lot of my friends tell me it looks like a donut. Okay? So basically, what we're seeing is light that is bent around the black hole to create this ring. And then in the middle is what we call the shadow, where if the light travels here, eventually it will fall into the black hole. Okay, and the size of this shadow is about 5 times the radius of the event horizon. Okay? And the event horizon radius depends only on the mass or how heavy the black hole is. Okay, so if we know how heavy the black hole is, we can calculate what size this shadow will be. Okay? And what do we know about this black hole? Okay? First, because we know its distance, we know that this size of the shadow is about 100 billion kilometers across. Okay, I apologize, I keep using billions today. I know you already have enough. Hear a lot of billions in the news recently. Okay? But, astronomy is, everything is very big, right? Okay? So, we know the size of the shadow, so we know the size of the event horizon, okay, which is about 2.5 times smaller, okay? Which is about 40 billion kilometers, which tells us that the event horizon of this black hole is just slightly about 3 times bigger than our solar system, okay? So it's quite huge, right? In fact, this is one of the most biggest black holes we know. Okay, and I said the size of this shadow depends only on the mass of the black hole, or how heavy it is. So from here, we can go back and calculate, right, that the mass of this black hole is 6.5 billion times the mass of our sun. Okay, this is one of the big black holes we know. Right, again, just to remind you, this is the mass of our sun, and imagine 6.5 billion times of this. Okay? What else do we know? This black hole is in the center of a galaxy that lies 55 million light years away. So which means the light that we see from this black hole, when we see this image, right, we are seeing light that has been traveling to us for 55 million years. Okay, like I said, light travels 300,000 kilometers per second. Okay? And light travels in 1 year, how much? 9,500 billion kilometers. That's how much light travels in 1 year. Okay? But now this black hole is located 55 million light years away. Okay, which means light from that black hole has been traveling to us for 55 million years. Okay, just about 10 years after dinosaurs went extinct. Okay, now we detect it in our telescopes. Okay? And this galaxy is called M87. It's towards the direction of the constellation of Virgo. Okay? And here we are zooming in, okay, to see this galaxy. Okay, here we see the galaxy, and there's a lot of stars, about a few 100 billion stars in this galaxy. And here you can already see the jet that is produced very close to the black hole, and the jet goes all the way in, okay, to the center. Okay, and now we see that it's actually produced by the black hole itself. Okay. So what is the use of this image, right? Okay, for one thing now, we have the first direct visual evidence that black holes exist. Okay, like I said before, we already believe that black holes, we accept that black holes are out there, they are real. But this is the first time we've actually seen one, right? Like we always like to say, seeing is believing, okay? So now we have the first visual evidence that black holes are real, okay? And now, using these black holes, they are tests, okay? They are like a laboratory. We can test Einstein's theory of relativity in very extreme high gravity conditions. And so far, we find that Einstein still passed his test, okay? He developed this theory about 100 years ago, okay? But his theory has not been dispelled, okay? All the tests we have so far shows that his theory so far is still correct, okay? Even in this extreme case, close to a black hole that's of this size, okay? And now we also have very strong evidence. We confirm that these jets, okay? I told you, show you these jets, right? And I said we believe that they can only be produced by the region close to supermassive black holes, okay? Now we can confirm that indeed these jets are produced and powered by supermassive black holes, okay? Other than that, before that, it could be anything, right? We couldn't know what's happening inside there, right? But now we know this is wrong, okay? Now we know it's produced by black holes and not Ultraman, okay? In fact, my Japanese colleagues tell me that this laser that Ultraman can shoot is called M87 beam. Okay, it's actually named after the M87 galaxy because of this jet. Okay? And, just this 1970s, this physicist from MIT, okay, Jim Bardeen, this is what he said, right? It's conceptually interesting, if not astrophysically very important, right, to calculate the precise apparent shape of the black hole. Unfortunately, there seems to be no hope of observing this effect. So 50 years ago, the idea is that there will be no hope ever of actually observing a black hole, okay? But now we can actually see a black hole, right? So how do we do it? Okay, how do you take a picture of a black hole? The first thing you can do is you take your DSLR camera, right? You fly as close as possible to the black hole, and then take a picture of it, right? Okay, but of course this is not practical. It will take too long to fly to the nearest black hole. Not to mention also it's very dangerous. If you watch Interstellar, you know. Okay, so what else can we do? Okay, we need to be able to zoom in very, very close to the black hole. We need to produce a very sharp image, okay? Those of you who do photography, how do you increase the resolution of your picture? Okay, you have a very big lens. The bigger your lens, the sharper your image can be, okay? The higher the angular resolution, okay? And to see the black hole in the galaxy M87, okay, you need to have a picture that is so sharp, okay, where you can actually resolve 25 micro arc seconds. Okay, which is 0.000007 degrees. Okay, this is equivalent to be able to see an orange on the moon from the Earth. So basically you need very, very high resolution. And it turns out to do that, we need to build a telescope the size of the Earth. Okay? Now, of course, we can't build a telescope the size of the Earth. Okay, you don't have enough money, right? Okay, so what do? You build pieces of it. This is the low budget kind. Okay, we have, 8 different telescopes, all right, placed all around the world, okay? And using these 8 telescopes, when you observe the object, you can combine the signals together to simulate a virtual telescope that is the size of the Earth, okay? We call this the Event Horizon Telescope. Okay, it consists of telescopes we have in Spain, in 2 of them in Chile, Apex and ALMA, LMT, in Mexico, SMT, in the US, and 2 more telescopes in Hawaii. Okay, and also 1 in the South Pole itself, right? And for a big global thing, you really need a big collaboration, okay? So part of this Event Horizon Telescope collaboration, there's about 200 of us, okay? And more than 13 stakeholder institutions, right? These including Asia, my institute. So these are the main institutes where we provide the telescopes, we operate the telescopes. And we have actually 62 affiliated institutes where most of the scientists come from, okay? So it's really, really a global effort, and it really shows what humanity can achieve when we come together as one, which is really important, especially these days we keep hearing in the news about, wars and trade wars and all this. While this is ongoing, we scientists just say, why not we come together and do something together, right? Okay, and of course you need a lot of money as well, and these are all the people who provide the money for all of us, and a lot of these are government institutes, so are basically paid a lot by taxpayers, which is why we do this kind of thing, because we think we're giving back to the community, right, who pay for us. Okay? So once you have the telescope ready, okay, the last decade they've been building all these telescopes on mountains and all this. What do? We observe, okay, the black holes. So in April 2017, we had our first observing campaign. Okay, so all of us went to different telescopes. I was here in Hawaii on top of the volcano Mauna Kea. Okay, it's about 4,000 meters above sea level. And it was a really, really interesting experience, okay, because the oxygen is about 30% less. And after a few hours, you already feel dizzy, and, that's why we have so many of us, just to make sure, check and double check everything. You can't think properly, okay? And we had 10 days to observe, okay? And you can be as prepared as you want, no matter how prepared you are, there's one thing you cannot prepare, and that is the weather, okay? And you need weather to be good at all 8 sites all over the world. That is very difficult. But fortunately, okay, the first 2 nights we had perfect weather at all the sites. That's why you see all blue skies everywhere. Okay? And we observed for a total of 5 days. Okay, and what do you do after that? We process the data. Okay, here's a picture of actually just half of the data. Okay, this was in Germany. So the data was actually sent from all the telescopes. Okay, we cannot transfer the data through the internet. Okay, why? This is a huge amount of data. Okay, one box of this, we call this a disk module. One of this is 64 terabytes. Okay, you look at this, and again, I said this is half of the data. Total is about 3,000 terabytes of data. We cannot send it through the internet, it'll take forever. Okay? And this is half. Half was sent to Germany, the other half was sent to MIT, where they have the supercomputers to process the data. So the highest bandwidth is not through the internet. To send this data, okay, the highest bandwidth comes from your jumbo jets. Okay, we ship the data from all the telescopes to MIT and to Germany, okay, in Bonn, to process the data. Okay, we play back the data, we combine the signals together, and then after that we work on calibration, and this was something that I was involved in, okay, to correct for all the instrumental effects, take out all the effects of the atmosphere. Okay, because all the telescopes are in different parts of the world, right? The atmosphere is different. So we have to take out all these things, and we spent actually just 1 year just to process the data, okay? And we went back and checked everything. If there's something wrong, redo again, And after that, what do we do? Okay, then we can make the images, right? And it's not so simple, it's a bit more complicated. It's not like just taking a CCD, capture the picture, and that's it. Okay, because like I said, we don't have the full telescope, right? We don't have telescope the size of the Earth. What we have actually is, imagine you have a lens, right? You break it into 1 million pieces, and you throw one piece there, one piece there, one piece there. You take the image, and you try to recover the image. Okay, so it's much more challenging, and we took a few months just to do this, okay? And because there are some assumptions and a lot of things that goes into processing, making the images, what we did is actually we have some blind imaging, okay? We sent the images, the data, to 4 different teams. Okay, independently, there are 4 teams who are making the images, using different algorithms, using different techniques, okay, with different people involved, and are not supposed to communicate with each other for a month. Okay, and we are all just making our images, and even within the teams, we ourselves started making our own images first before we can talk to each other to compare our images, okay? And so here was my team, okay, led by Shoko and my institute, and we made our images, and after we saw the images, when we saw this ring shape, all of us got very excited, okay? So to celebrate, they were at a conference in Korea, they took a picture together and had this secret symbol, okay, to say that we have seen a black hole, right? But unfortunately, I wasn't there, okay, I was in Greenland at the time. So they told me to do this, take my picture, and then send the photo to them, and they'll do Photoshop my picture in, okay? And this is their level of Photoshop. I'm sure the FCM people here can do much better than this, okay? And here's Hiroshi as well. He was in Japan at the time who couldn't join. And this was when we compared our images for the first time between ourselves in our own team, okay? But after that, the 4 different teams, okay, from Europe, US, and all of us, we compare our images, and all of us saw this ring-like shape. Okay, and now we are confident, even though we use different techniques to image, even though we have different, assumptions and all this, all of us see something that is consistent. That's when you know that it's real, okay? Not something that you see because you want to see it. Okay, and this is the first time when all the 4 teams, we came together to combine and share our images, okay? And once we are sure that we are seeing what we're seeing is real, we all meet together this was in Radboud University in Netherlands. Okay, I'm here. Botak, just look for Botak guy, okay? And here's where we discuss, debate and analyze our results. We actually still produce thousands of images. We try to improve on our images to find what is the best ones. Okay, and when you're done with that, then you publish your paper and have a press conference, okay? So we had 6 press conferences all over the world. This was the one in US. This is Shep, our director of the whole EHT, right? And this was the press conference in Washington, D.C. And of course, we also had our press conference in Taiwan, okay? And for the first time, I get to sit in front there. And I told Jijian, that there's only 2 times in my life, or now 3, where I'm actually wearing a coat, okay? My wedding and this press conference. And now this is the 3rd time I'm wearing a coat, okay? Because astronomers, usually we don't wear coats. We wear shorts and slippers for conferences. Okay, but the president of our academic sneaker asked us to wear. Okay, and of course, this thing really blew up. It really blew up beyond our expectations, We collected all the front page newspapers, all over the world, with the image of the black hole. And even, the president of Taiwan, she put it on her Instagram, okay? And our press conference in Taiwan was actually streamed live, and we actually had 1 million viewers, which is quite a big population of Taiwan, like close to 5% of Taiwanese population. Okay, and of course, you've made it, okay, when Google puts you in one of their, these things, okay, now you know it's a big thing, okay, when Google puts you there, okay? And of course, as expected, these things became memes and all that on the internet. And you can see, some people at least were disappointed with the image, right? Commercial versus reality, right? Of course, all these things came out in my internet feed. Even Durex also decided to get involved. I don't know what this means, okay? And I think in a few days after we published our results, right? I think I saw 4 more black holes images on my Facebook feed than the 8 months that I spent before that working on the image, okay? And I think some of us even probably got sick of seeing all this, okay? Now, this is something that's been going on for a long time, okay? This is what we observe, but our theory, our models tells us this is what we're supposed to see. And this is a poor, lousy version of this, right? Okay, the reason is that we don't have enough resolution yet, okay? To actually get a higher resolution, we need to improve this telescope that we have. Okay, so since, for a while, we've actually been, even as these observations were ongoing, we've already been trying to improve the telescope, okay? So if you blur it to the resolution of our telescope, this is what you expect to see, right? Okay? So the M87, the black hole image we saw, was observed by these telescopes, okay? Now we're trying to improve the resolution by increasing the distance between telescopes. And we're putting more telescopes, okay? Now one in France, okay, another one in the US, and now one in Greenland. And this is a project that I'm currently involved in, okay, with my institute and together with Harvard-Smithsonian Center for Astrophysics in the US, okay? So what we're doing is we're building a telescope in Greenland, in the Arctic, okay, and now the telescope is here in the US Air Force Base, okay, where we're testing everything. Eventually, our plan is to move the telescope to a mountain in Greenland. It's about 3,000 meters above sea level, okay? But now, so far, we are doing everything here in the base where there's still a lot of facilities, okay? So in 2017, all the construction was going on, and by July, okay, 2017, the whole telescope was done, okay? In summer by all the engineers in our institute, okay? And just within a few months, okay, we went there and installed, put the software in, put all the, check the accuracy and everything, okay? So that was what we've been doing for the last few years, right? And Christmas Day itself, okay, we had a very nice gift. We had what we call the first light. Okay, whenever people build telescopes, right, there's this very important milestone which we call first light, which means you put everything together, the receivers, the dishes, everything. You put the software in, then you point it as an astronomical source for the first time. So here we pointed at the moon. Okay, and then you switch it on, and you see the signal, and then you have a huge sigh of relief because you know everything is working. Right? Of course, it's not there yet. There's still a lot of things to do. But we detected the moon and we celebrated. Okay, this was a really great Christmas gift. Okay, for us. And of course, everybody was home celebrating Christmas, right? Just me and my boss, two lonely people in Greenland. 24-hour darkness, no light at all, minus 30 degrees Celsius. Okay? So, watch out for the bears, yes. So before we went to Greenland, all of us have to go through a training, right? And one of the training, 1 hour, is just what to do when you see a polar bear, okay? And they have steps, depending on what the bear is doing, if he's doing this, if he's looking for food or he's taking care of a baby. So there are different steps of what you can do, spray the bear spray or whatever. And the last step is the fight. I saw a fight with all your might. Your life depends on it. That was on the slide, okay, during the training, okay? But actually a few days later, after our celebration, okay, there was actually a big disaster at the telescope. And I said I really have to tell this story here because it's the time when MMU, saved the Greenland telescope, okay? So what happened? Okay? So what happened? So when this telescope, when it points up 90 degrees, that's when you can actually access, you can climb up, this is about 2 stories high, you can climb up into the cabin, we call it the receiver cabin. That's where all the electronics are, the receivers, okay, all the expensive stuff basically. And all this operates in room temperature. Okay, so what happens is that inside this receiver cabin, we have a special heating system which heats the cabin up to 20 plus degrees, okay, room temperature. And but of course, outside is minus 30 degrees Celsius, right? But we got some problems. We got some signals showing some alarms going off. We were investigating. Later, we found out what was happening was that something had exploded, okay, and burned the heating system, okay? And, a lot of the wires all were melted, and some of the wires had fused together. There were some short circuits everywhere, okay? And it was just me and my boss, 2 of us there, and of course, we are astronomers. My boss is an astronomer, right? And all the engineers were elsewhere because it's Christmas time, okay? And we had to try to solve the problem, and this heating system, okay, was actually built by a German company. And you all know the Germans, right? They take their holidays very seriously. Okay, so this was just between Christmas and New Year. None of them were responding to emails or everything. So we contacted our engineers in Taiwan. They were trying to read the schematics and tell us what to do. Okay, and it was just 2 of us trying to, in the end we had to cut wires, reconnect wires and everything. And I was because I had this engineering degree from MMU, so I was the one doing all these things. But I was so stressed because, I've never touched a multimeter since my lab days 10 years ago in MMU, okay? How to use multimeter, I was channeling all my memories, all the things which I already throw back to all my lecturers, right? Okay? And, at least we still remember how to strip the wire and connect them like last time in the lab. Okay, but in the end, and this was very stressful because we were also running against the clock. I felt like I was in a movie, okay, where you're like a bomb squad. Because we could see the temperature of the cabin was going down, okay, 20 to 10 degrees, 9, 8, 7, and a lot of the electronics in the room, the specifications say that, they do not operate below 0 degrees, okay? A lot of them can get damaged and they cost millions, okay? So we were running against the clock to try to solve everything and fix everything, okay? And we were running up and down, so the control room where we have the internet and can contact the engineers, run up, run down, run up, run down, I think about 100 times, and it was so cold, okay? But eventually, we didn't manage to fix it in time, because, if it was a bomb, I would have been dead, So eventually, what we had to do, okay, when you can't do it on time, what do? You call the military. I said, this is the Air Force base, right? So we borrowed, actually we rented, it cost a few thousand US dollars per day. you rented one of their generators, okay, which pump and then pump heat. Okay, these are heaters. Me and my boss, two of us, dragged this whole pipe that was this big, drag it up into the room up there and turn it on and heat up the room. Okay, and it made it more comfortable for us to work inside also lah. Okay, but eventually we managed to sort of stop. Okay, and then get it back to the state where, we can heat up the room and not, spoil and destroy the electronics, okay? So, yeah, I thought I should tell this story. And just to show how cold it is, okay, this is the rime ice. Okay, there's on all the stuff everywhere, okay? So I thought I'll share a bit about, what it's like to live in the Arctic, right? So, of course, in winter, you get 24 hours darkness. So the people that actually take care of the soldiers, the Americans take care of their soldiers very well. You get to play all these for free. No need to put coin inside, okay? You play game, can continue forever until the end of the game, all right? Okay, and they actually have a swimming pool, a gym, a bowling alley, and you have DVDs. Okay, my boss actually watched the entire, Game of Thrones all there. Okay, and you have nice, cafes. There's even a pub there, all right? And yeah, you can, okay, of course, in winter, you only stay in the base, right? But in summer, you get to go out, okay, and explore. Okay, you get to go visit the glaciers and, see all these kind of things. And this is the sea, okay, which is frozen. This is like about March, where the ice has not melted yet. So the sea is still frozen, so you can go swimming on the ice, okay? So, a tip for you all, if you want to go to these kind of places, go Greenland, South Pole, go Hawaii all the time, be an astronomer, okay? And of course, we've had lots of visitors. Some of you might recognize Neil deGrasse Tyson, okay? He was there to film a documentary for National Geographic. Okay, so of course, I'm a fanboy, go take picture, selfie, all that. Okay, and we also had Nikolai Coster-Waldau. Okay, some of you will know him as, Jamie Lannister, right? He also was doing a documentary, a Danish documentary. He also visited our telescope to do interviews and all that. Okay, and I go end with my last point, okay? Malaysia boleh, right? And, a lot of, I don't know, some of you will go on social media, right, or what? Sometimes it can be a very bad place, lah. Malaysians, right, somehow like to kutuk everything, And a lot of times we all local grads always kena kutuk, right? We always kutuk local grads, or the overseas grads are so good, whatever. But I'm a local grad, okay? But, Malaysia boleh, Okay, and for me, I'm just one of many Malaysians, okay, who are out there contributing our part in the world. Whether we're overseas or here, all of us are doing our part, okay? And here I'm just showing a sample of some of the astronomers, okay, Malaysian people who are contributing to astronomy. Here we have Dr. Adlika. Now she's known as the Ratu Lohong Hitam in Malaysia, right? Okay, and she also does research on supermassive black holes. We have Chin Fei, who's actually my institute's deputy director. Vinod, who works for the European Southern Observatory. And Jensen, okay, who is a Hubble Fellow. Hubble Fellowship is one of the most prestigious fellowships in all of astronomy all over the world. Okay, and here he's a Malaysian guy, okay, with a Hubble Fellow, and now he's based in Princeton. Okay, and Dr. Zamri, all these people, we have Malaysians from all diverse walks of life, okay, whether you are Melayu ke, China ke, India ke, really nobody cares, right? And you have people who have all sorts of backgrounds who have made it and are working in astronomy, in their day-to-day lives, okay? And I would say it's never too late to start, okay? And I'm a big example of that, right? As you all know, I was here in MMU doing engineering, right? Okay, and even for my master's, I was doing engineering, working in the rice fields. Okay, I was doing remote sensing, okay, using satellites to measure, the density of rice fields and all these things. And after that, from there, I moved on and I decided to do my PhD. I thought, why not do something you really like? Okay, life is too short, okay, and I really didn't really like engineering that much at all, okay. So I decided to do radio astronomy, okay. So, which is very closely tied to electrical engineering because the first radio astronomers were actually electrical engineers, okay. And I did something pretty close. I was looking at how waves, okay, interact with rice fields. Now I look at light and waves, how they from black holes, how they interact with gas in our galaxy and all that, okay? And after that, I moved on to study black holes and do research on all this black hole stuff and got involved in this project. Okay, so it's never too late. Even when I was doing my PhD, there were Australians there who were retired engineers who wanted to learn more about astronomy, and they were doing me at the same time with me, okay? So, yeah, if you want to, there's nothing stopping us, right? Okay? So I think I'm going to reach the end, and I'm going to say that for those of you who want to find out more, right, there are books you can read, okay? These are some I recommend. Some of these are more technical level. Okay, you can visit our website for updates for the Event Horizon Telescope. This is a very good documentary, I think. Okay, that was made by BBC. It was published just a day after we presented our results, okay? So when we were observing, they were actually filming us. Okay, and this is a BBC documentary, 1 hour long, and I watched it already, okay? And I realized I was actually in the documentary for 4 seconds, okay? I was in 4 shots and in 4 seconds, okay, cukup lah. Okay, and for those who know Chinese, this was actually done by a Taiwanese group about the Greenland telescope, okay? Some of the interviews are in English because most of our team, a lot of them are Japanese, but those who can understand Chinese, you can go watch this on YouTube, okay? I don't even know how to read this, because I'm from SK, okay? So my Chinese tablet pakai one lah. Okay, and so I end, okay? So this is the iconic image we have, and that's how we got it. And yeah, feel free to ask me questions, okay? All right, thank you. Thank you.
Thank you very much, Dr. Kevin. So yes, Malaysia boleh, and MMU boleh. Right, we have a few minutes to take some questions. So do we have any questions from the floor? Before you, please proceed to the mic, introduce yourselves as well as where you come from, your affiliations, before you ask the questions. We have 3 mics, center, right and left. Introduce yourself and where you're from.
Hi, my name is Alvin. I'm from EMOS. First question is, what are the error bars like on the observables from the different computational runs? How close or how far did the independent computations come when it came to figuring out what the black hole physical parameters were, mass and rotation and so on?
Okay. So thank you for the question. Actually, I don't have the slides for all those here, but for the other talk that I'm giving at 2 o'clock, which is a more technical one, I have all those slides that show the error bars for the black hole mass and all these things. But yeah, you're right. There is some uncertainty in the image itself, like what do we know is real or not real or things like that. So we actually made a lot of trial runs with our algorithms and tweaked the parameters, okay, to compare. When you have different parameters, what kind of image does it produce? Okay, how certain can we be on this feature of the image and another feature of the image? Okay, so after doing that, let me see if I can go back. So these were some of the preliminary ones, okay? So here you can see it's still some of the early stages of our imaging, right? But even then, we can already confirm that the brightest component is always towards the south. It's always brighter in the south and weaker on the top, okay? And this is one of the only features that we can say with certainty.
Is that because you were observing it like not completely perpendicular but edge on?
Okay, so the reason for this is actually the orientation of the black hole, of the jet and all that. And we actually know it's actually rotating. Okay, so the black hole is spinning.
Okay.
And from this feature, right, we know that the black hole is actually spinning clockwise. Okay, and the bottom part is moving towards us, and the upper part is moving away from us. Okay, so here is boosted, okay, and more power when it's moving towards us, and it's weaker and it's moving away from us. So this feature we know is confirmed, okay? But there are some features, some images, for example, you see there is some bright spots here. Here also you can see some bright, but others they don't have. So some of these features, we are not sure if it's there. Okay? And that is because we have all this missing information, because we don't have information at every single point on the Earth. Okay, so yeah, here I can't show you much. The other slides that I have, I can show more details about all the different images we have, but what we published were the features that we can see with certainty. Okay, and there is this.
Can I ask a related question on that matter?
Yeah.
You have a slide about the network of your telescopes, right?
This one?
Yeah. I guess this is optical wavelength, so you're only selecting locations on one hemisphere that has a nighttime view at roughly the same window of time.
Okay, so this is not optical, okay? So I didn't mention this, but we are observing in millimeter wavelengths, so it's at 230 gigahertz. Okay, and at this frequency, actually, the light, okay, although it's traveled for billions of light years, the light gets absorbed by water vapor in our atmosphere. So the sites for all these places are selected to be either very high mountains or very dry sites where, for example, in the South Pole, all the water and atmosphere is locked in the ice, right? And all these places, they are about at least 3,000, 4,000 meters above sea level. We are above some parts of the atmosphere, so the absorption is less.
Any particular reason why you don't have any sites on the backward hemisphere of the Earth?
Okay, so because they need to observe the object all at exactly the same time. So we actually found that Nepal was also a good site, okay, but we can't observe together at the same time with all these telescopes. So we need the observations to happen exactly at the same time, down to microsecond level. That's why each of the telescopes, we have a hydrogen maser, an atomic clock, to keep time down to the microsecond level. And after that, when you combine the signals, they have to adjust, okay, exactly down when they combine the signals. So we cannot have telescopes on the other side of the Earth. Yeah.
Okay. Thank you. Right. Do we have other questions?
Can I ask one more while we're waiting for other people to come?
I think we have the people there. Right. On the extreme right.
Hello, my name is Mohammed Al-Badri. I am third year student FOE. My question is, Einstein have represented...
Can you speak louder, please?
Yeah. Einstein actually gave us the mathematical representation for that there is a black hole. So how did you know that the black hole is over there in exactly this place while it's so far from the Earth? About the second question is, for example, if you bring any normal camera and you just zoom until the end, you're gonna lose your goal. So how did you keep your focusing on the black hole while it's like 55 million years, light years?
Okay, so the first question is, what's the first?
How did you know that there is a black hole over there?
Okay, how do we know to observe there?
Yeah.
Okay, and not elsewhere in the universe, right? Okay?
Yeah.
So actually, we've been looking, and we already, like I said, we already believe that in the centers of these galaxies, there are supermassive black holes, okay? But why did we pick this one, okay? Because we have been trying to measure the mass of black holes, okay, using other techniques. Okay, for example, we measure how the stars are going around the black hole, or how the gas is going around the black hole, to try to estimate how much mass is in there. And of all the black holes we know that are nearby us, so this is actually, I say it's 55 million light years. Seems very far, but in astronomical terms, it's actually one of the very nearby galaxies. Okay? This is one of the two black holes we know so far where they are big enough where we can actually see the shadow. Okay, the other black holes, either they are too far away or the black holes are too small. They are not as heavy enough. Okay? So there's two that we know. One is this one, M87. The other one is the black hole in the center of our galaxy. Okay, and we are still working on that data right now, actually. Okay, for the one in the center of our galaxy. And the second question is...
Second question, how to keep focusing on the black hole while the Earth is spinning all the time? And how did you focus on the black hole all this time?
Okay, so while the Earth is moving around, right?
Yeah.
Yeah, so actually, all these telescopes, okay, this is already a very common thing in astronomy. When we observe astronomical objects, we have to point, and we have to track the objects in the sky, because the sky is moving, right? Just like the sun rise and set, because the Earth is rotating, all the stars, all the objects, because our Earth is rotating, all are moving across the sky. So we have all the software and all the telescopes that tracks all this across the sky, following a model of the Earth's rotation and the Earth's movement around the sun. And it also takes into account that the Earth's axis is precessing, okay, it's tilting all the time. And there are a lot of things you have to consider actually, okay? So all these are already included in the software so that it tracks the telescope. It tracks the object, okay, the black hole. Okay?
Okay, thank you.
Yeah.
All right, thank you very much. We've got some question there on my right, the gentleman in the gray shirt. Yeah, right.
Hi there, my name is Manoj Kumar. I'm a new student from FOE. Why can't we use the sun as the reference point?
Okay, why can't we use the sun as a reference point for like the GPS and all this? Is that what you mean? Okay, number one, for one, the sun is too big. Okay, you need a point on the sky, right, to be an accurate reference point. The bigger it is, the bigger the inaccuracy of where exactly you're talking about, right? Okay, and of course, the Earth is always moving relative to the sun. It's always moving in the sky, right? So you can't use it as a reference point. You need something that's fixed in the sky, okay?
Okay, thank you.
All right, one more on my left or center.
Hello, I'm a student from Faculty of Engineering, Multimedia University. Thank you for the talk. Since this isn't a technical talk, I'll just ask a simple question. My question is, can we travel through a black hole like we have seen in the Interstellar movie? Related question, what happens to time inside a black hole? Give me your opinion since you have a first-hand experience. Thank you very much.
Okay, so can we travel to a black hole? I think the nearest black hole we know is a stellar mass black hole in one of the stars, close to nearby. I think it's just a few light years. Okay, but even then, if we can travel at the speed of light, it will take a year or a few years to get there. And of course, we can't travel that fast yet, so I think right now it's still not practical yet, but maybe in the future, who knows, right? But what happens to time inside the black hole? And my simple answer is I have no idea, right? We know what happens when you go close to a black hole, okay? Einstein's theory of relativity tells us that the stronger the gravity is, okay, time will slow down relative to time elsewhere where the gravity is not as strong. So as you go closer and closer to the black hole, time will move slower and slower for you. Of course, you won't realize it, but from Earth, if you observe, okay, you will see that you are slowing down and going in slow motion, okay? But what happens after you go in, I have no idea, and I have no theories for how that works.
Sometimes it's said that time and space trade places inside a black hole. Like, what does that even mean? Does that even mean?
I have no idea too. Okay, but from Einstein's theory, we know that space and time are just different dimensions of the same thing, right? It's a four-dimensional space-time universe. So, yeah, that's all I can say.
Thank you very much.
All right, thank you very much. We'll take question from my left side of the hall here.
Hi, my name is Omar Suleiman. I'm from Adni Islamic School, Ampang. Sorry, I might have missed this, but how exactly do all of the telescopes function as one telescope, as a global telescope?
Okay, so how do all the telescopes function as one telescope, right? So basically we have these telescopes all over the world, right? But all of them are controlled individually, okay? So we were there in Hawaii, we control the telescope from there. They will control the telescope from everywhere, okay? And we will just have like a timetable or schedule that between this time and this time you point at this object, between this time and another time you point at this object. So that's what we do. We just move the telescopes around. But of course we have the control center in Boston, in MIT, and they will tell us, if there's any changes, or they'll monitor the weather all over. Okay, and what we do is actually we just record the data into the hard disks that I show. Okay? We record the data here, then after that, okay, at the supercomputers, we actually, what we call do a playback or adjust the timing, the timestamp, okay? Adjust the time so that we can combine the signals from all the telescopes at exactly the same time that they were observing, okay? If you don't do that, you can't detect any signals. Okay, the timing has to be exactly accurate down to micro-arcsecond level. So we combine the signals from the telescope using supercomputers. Okay? Yeah.
All right, we have time for one more last question.
Okay, hi, my name is Farah, and I'm from Adni Islamic School. My question is, if an explosion from the supernova happens, what are the probability of the black hole to form?
Okay, so in all my experience with giving talks, right, usually the students and the children are the ones that ask the hardest questions, you know. And they are the ones who know more about black holes, probably more than me, okay? So now, a supernova, okay, some of you who may not be familiar with the term, that's what happens when a star that is at least 5 times, okay, more massive than our own sun, okay, explodes. They reach the end of their life, they have no more fuel to burn, okay, everything collapses on itself, okay, and gravity pulls everything together, and after that, you know, it explodes and releases a lot of energy, okay? Now, supernova, we know, they actually turn into black holes, okay? Like for example, for our sun, because it's not massive enough, it won't turn into a black hole. We believe it will turn into a white dwarf, okay? Now and our sun probably won't go supernova as well. They will eject all these gas in what we call a planetary nebula. But anyway, for supernova, okay, that means if a supernova happens, it means that it's most probably going to produce a black hole, okay? Probably it will be a black hole because to have a supernova in the first place, this big explosion, the mass of the star needs to be at least 5 times that of our sun, okay? So it will produce a black hole, right? That's what we believe, lah.
Okay, one last question.
Thank you very much. Suleiman Mansari, a guest with respect to the Malaysia Technical Cooperation Program doing design thinking and business model canvas here. My question is, the photos you have from the different teams, did you try to superimpose them?
Okay, so actually, so you see this image here that we did, this was actually the average of all the images that we made before. But again, this is not our final images, okay? This was just a preliminary one that we're sharing for the first time. We only spent a few weeks on this. Okay, later we actually improved our techniques and algorithms to get much better images. And the final image that was published actually is the average image over all the 3 different techniques that we used.
Okay.
Okay?
Thank you.
All right, okay. I believe, do we have any other? Okay, we have a question.
We have a question from our little friend. Please.
Okay, from our young friend there.
Hello, I'm Mariam and I'm 9 years old. I'd just like to know 2 simple things. You know when you took the photo, how much did you spend in total to get that photo of the black hole?
Okay, so that's the first question, right? So how much do we spend? I don't know. I have to ask my boss, ask the director, but because what happens is that all these telescopes, they are not actually built specifically for this project, okay? These are all telescopes that are already built for, you know, to do other things. Okay, what we did was just implement some new hardware that was needed to record all the data, okay? And so these are, again, you know, some of these cost like millions, few millions of dollars, right? But they were already there, and we didn't pay for those. Okay, what we paid for as a collaboration was mostly for the hardware and also manpower, you know, human resources. Okay, and how much is that? I have no idea, right? Have to ask the upper, you know, directors and all this. For us, we worry about the science, and we let the big guns up there worry about the money. Okay. So, but yeah, sorry, I cannot answer that.
How long did it take to put all the data together?
So you can see, we did our observations in 2017 April, okay? And we published our results in 2019 April, right? So it took us 2 years, okay? Now one thing actually, it took much longer than it had to because, like I said, we had to ship the disks to the supercomputers, right? And there are no flights to the South Pole in winter, okay? And in April, of course, it's winter time in the South Pole, right? And we actually had to wait until September before flights went back to the South Pole. And we had to wait until then before we can get the data for the South Pole. So the people who were there, they were there for the whole winter time, for a few months. Okay, so we waited for that, and after that, like I mentioned, we spent just 1 year just to check everything, the data, because we know this is possibly a very important result. And the more significant it is, the more careful you have to be with the data, right? So we checked everything, double check, triple check. We checked everything 4 times actually before we released the data to make the images. And after that, it took about 8 months to finally make and confirm the images and analyze the results. So in total, about 2 years, okay? So it's a long time, yeah.
Thank you.
Thank you.
Thank you very much. Thank you very much, Dr. Kevin. Ladies and gentlemen, a huge round of applause.
Thank you.
Dr. Kevin. Right. Dr. Kevin, you might want to stay on stage for a while. Okay. Distinguished guests, ladies and gentlemen, it is our honor to now call upon Professor Dato Technologist Dr. Ahmad Rafi Muhammad Esa, President of Multimedia University, accompanied by Dr. Uy, Dean for the Faculty of Engineering, to present our speaker, Dr. Kevin Koay, with the Alumni Achievement Award. Ladies and gentlemen, for your information, this special award is designed by our third-year FOE student, Mr. Benny Wong, who is carrying the award right now. Thank you very much. Right, please remain on stage, Dr. Kevin. We would like to invite Dr. Shamimi and other distinguished guests on stage for a photography session. Prof. Hairo.